Okay, so hello everyone, and we will have Shayan and his fourth lecture on polynomials and algorithm design. So Shayan, please.
Hello, welcome back. So in these last two lectures, we're going to switch gears and we're going to talk about a different class of polynomials called log concave polynomials. So the real scale polynomials I talked about in the first three lectures are mostly, the theory were mostly developed maybe between 2005 and 2010 by numerous works of Borsia, Brandon, and Tom Liggett, and many others, David Wagner, Sokol, and so on, Koi. The log concave polynomials theory is much more recent. It's been developed over the last 2-3 years. And so, okay, so I'm going to motivate it and tell you the goal in a second. So let me just remind you a few facts we have said before. So we said that, I mean, I didn't prove it formally, but it's in the notes that if you have a real set polynomial with non-negative coefficients, it's log concave over the non-negative orthant. Okay, so this non-negative coefficients show up a lot in this lecture because whenever you want to talk about log concave polynomials, I want the polynomial to be non-negative over the whole orthant. Okay, because if the polynomial is negative at some point in the positive or at some point in the domain, then the log is not well defined, and I wouldn't be able to talk about log concavity. So I want to assume that coefficients are non-negative to make sure everywhere in the positive orthant I have a non-negative. My polynomial evaluates to a non-negative number. Okay. So real estate polynomials are log concave. Now, again, if you have forgot about log concavity, that means that if you take the log of p, it's a concave function. Okay, so that's what it means. It's a concave function over the positive orthant. So, I mean, again, just to remind you, it means that for all the log concavity of P means that basically log of P at A, like half of log of P at A plus log of P at B is bigger than or, no, it's less than or equal to log of P at A plus B over 2. Sorry. Okay, so it's another definition of log concavity, so meaning that the log of the function is concave. Now, if you take convex analysis courses, you see that there's an equivalent definition for log concavity, which is that the function is log concave, or a function is concave if the Hessian of the function is negative semi-definite. Okay, so the same holds for log concavity. So P is log concave over the positive orthant if the Hessian of log of P is negative semi-definite as a matrix. So remember, again, if you've forgotten this Hessian, the Hessian of log of P is a, let's say at A, is a matrix in, it's an n by n matrix. And the ij coordinate of this matrix is equal to partial zi partial zj of log of P, and then you evaluate it at z equal A. Okay, so that's the matrix I'm talking about, and you want this matrix to be negative semi-definite. Okay, yeah, so just one definition that we're going to work in this lecture with. I'm going to say a polynomial is log concave just at one point A in the positive orthant if the Hessian of the log at A is negative semi-definite. Okay, so in general, you want the function to be log concave at every point in the positive orthant, meaning that you want the Hessian of the log to be negative semi-definite at every point in the positive orthant. Any questions so far? So let me now tell you, why are we interested in these objects? What are we planning to do? So motivation. So if you remember in the first lecture, I said that I said this. I mean, informally, I said this theorem of basically it's by Brandon, who said that there are matroids, such as Fano-matroid, for example, which are not realizable as the support. Let's say bases are not realizable as the support of a real state polynomial. Meaning that there is no polynomial for whatever coefficients that you plug in, there's no polynomial with a support the same as the basis of a Fano matrix. Now, when we started to work on this new class, this definitely was a sort of limitation, a big limitation to this class of polynomials. The point is, many of the theories. I mean, I didn't. Okay, I told you a little bit about applications, but there are many other applications of these real estate polynomials, and in many of them, it seems apparent that the machinery that we were developing should generalize to all matroids, not just say spanning trees or partition matroid and so on. It should generalize to all of them. And so we were looking for a class of polynomials which can capture all of them. And it turns out that log concave polynomials are exactly what we were looking for. Okay, so so in fact, we're going to show that. So the goal is to show that. So basically, we've just started the main theorem of this lecture is that for any matroid, again, if you don't know about the matroid, please look at the background lecture on matroids. So for any matroid m equal n comma I, so it has elements 1 through n and independent sets I. The generating polynomial of the matroid, the generating polynomial of basis of m is log concave. Okay. So I mean, g of m equals summation of b, which is a base, z to the b. Okay, so this is the main theorem. So this polynomial, so in particular, not only you can realize every matroid as a support of a log concave polynomial, you can also realize it as a support of as a polynomial where all coefficients are 1. Okay, so so this polynomial is not real stable even for not just for Fano matroid, for much wider classes of matroids. For example, even if you look at a graphic matroid, but not sort of truncated on subsets smaller than spanning trees, for example, you get counterexample. If you just consider a random set of vectors in Rn and look at the generating polynomial of the bases, most likely you don't get real stability. Okay, and again, I discussed this a little bit in the background notes. One reason that many of such polynomials are not real stable is that if you choose many of the matroid, is that real stable polynomial has a property that called negative correlation. I didn't talk about it in the lecture, but it's in assignment 1. You prove that real estate polynomials, or basically strong Rayleigh distributions, are negatively correlated. Now, it turns out that the uniform distribution over basis of many matroids is not negatively correlated. Therefore, you shouldn't get real stability. But log concavity, on the other hand, doesn't imply negative correlation, and therefore it has the capability. In fact, it captures all of the matroids. Okay, so let me start and see how. So I want to basically pave the path, build up machineries to prove this theorem. Okay, so let's start with something very simple. We're going to start with degree 2 case. Okay, so let's say you have a polynomial p. Sorry, let's say we have a polynomial p equal, it's a degree 2 homogeneous. It's equal to ZQZ. Okay, Z transpose QZ, that's what I mean. So it's basically equal to summation of ZI, ZJ, QIJ. Okay, so degree 2 homogeneous polynomial. Then, okay, so now, and let's say it has non-negative coefficients again. So basically, it means that Q has non-negative entries. So now we have this lemma, which says the following are equivalent. One is that P is log concave. The second one is that this matrix Q is negative semi-definite on QA perp, which is basically all vectors, let's say B, such that B transpose QA is 0 for all A in non-negative. Oh, and basically I also want and Q of A is non-zero. So what does this mean? It means that when I say negative semi-definite on this, it means that basically any vector, this is a linear space. It means that any vector in this linear space you choose, the corresponding quadratic form with respect to that vector is non-positive. Okay, so it's not negative semi-definite over the whole Rn, but it's negative semi-definite over this linear subspace. The third property is that Q has n-1 negative, or say non-positive eigenvalue and 1 positive. And then the fourth one is that P is real stable. Okay, so basic. Sorry.
But Tyler, you can answer pose the question.
Oh, there was a sorry.
Just what is little q? 0.2.
Oh, sorry. It should have been P.
Ah, okay, good.
Yeah, please unmute yourself. I sometimes don't get a chance to look at the chats. Okay, so basically what this lemma says is that, I mean, at the very least, it says that for degree 2, log concavity is the same as real stability. Okay, so basically, let me just, I'm not going to prove this as a whole. So I proved parts of it. So we saw basically, I mean, we didn't see, but at least I proved in the notes of previous lectures that four implies 1. Real stability implies log concavity always. So this one we know. Let me discuss how you go from 1 to 2. Okay. So, and the proof will be sort of illuminating. So how would you go from 1 to 2? The idea is that you want to look at the Hessian of the log of P. You can write Hessian of the log as follows: for any polynomial, for any polynomial, Hessian of the log is equal to at A is equal to P of A, Hessian of P, minus gradient of P transpose. This is evaluated at A. Everything is evaluated at A. Just do it at the end. Transpose over P, and then you evaluate P squared. And evaluate it at A, Z equal. Okay, so this is, here I'm not doing anything fancy. This is just rules of derivatives. You can just prove it for yourself. So this is always the case. Now, remember, gradient is a vector, right? You have just partial zi, partial z1, partial z2 to partial zn. So here we have gradient transpose, which gives an n by n matrix. Okay. Now, so now in our case, what do we know? The gradient of P is, remember, P is z transpose qz. So the gradient of P is exactly equal to twice Q matrix times gradient at A, twice QA. Okay. Now here is the point. Suppose let's say you have this vector B in QA perp.
Sorry, can I just ask? So if we have a mixed term, where do the two come from?
You have Z transpose QZ, right? You're taking the derivative, you get, this is Z squared basically. That's how you get the two. Yeah,
but so aren't there terms that are not, I mean, that contains, for instance, C1, C2 or something like that?
You have terms that in P you have Z1, Z2 terms, but when you differentiate, one of them will go away, right? You only have you only get one Zi, and then you substitute A, so you get A. So Z1, Z2, you get it twice, right? You get Z1, Z2 twice. You get Z1, Z2 times Q1, 2 plus Z1, Z2 times Q2, 1.
Right. Okay. Yeah.
Okay. And that's why you get the factor 2. And then you also get Z1 squared. So when you differentiate it again, you get 2 Z1. So everything, there's a factor 2 you can factor out. Good. So now if you have B in QA perp, I mean that B transpose QA equals 0, then basically B transpose the gradient of P at A is 0. Right? So now, therefore, for any such B, I want to look at B transpose the Hessian of the log at A, B. Right? This is exactly equal to the following, is equal to P squared, P times, let me write, okay, P squared of A, P of A, times B transpose Hessian of P A, sorry, Hessian of P, at A, B, that's it. Because the other term will vanish. The gradient times B is 0. So it's exactly equal to this. And now what do we know? We know that the Hessian of the log is negative semi-definite. So this quantity here is less than or equal to 0 for any vector, in particular, because it's for any vector in general, but in particular for B's which are orthogonal to QA. So this is less than or equal to 0. And now the only observation you want is that P of A is non-negative because basically P has non-negative coefficients. And Hessian of P of A is exactly equal to Q. Okay, so you just get basically that B transpose QB is less than or equal to 0. Okay, so this implies that B transpose QB is less than or equal to 0. Okay, so that's the 1 to 2 part. Now, the 2 to 3 part, let me just say that for 1 second. 2 to 3. So now let's look at the lemma again. So 2 says that on this linear space, the polynomial, the matrix Q is negative semi-definite. Now, if you think about this linear space, this has codimension 1 or dimension n minus 1, because you have just you're fixing one vector, looking at everything orthogonal to it. So it has dimension n minus 1. So you have this n minus 1 dimensional space on which the matrix is the quadratic forms are non-positive. Now, if you plug this in to the so-called variational characterization of matrices, again, I discussed it in the notes if you want to take a look, but or Rayleigh quotient, this immediately says that the matrix Q must have n minus 1 negative, or in fact non-positive eigenvalues. Okay. So basically by variational characterization. I should say I said one positive eigenvalue. How do you get the positive eigenvalue? The positive eigenvalue comes from the fact that Q has non-negative entries. So if you have a matrix with non-negative entries, this is by what is the theorem?
Frobenius.
Yeah, exactly. From Frobenius theorem, you get that it must have one positive eigenvalue. So so by from Frobenius, Q has one positive eigenvalue. Okay, and now the 3 equal to 4, the 3 to 4, I'm not going to prove it. That you can do for yourself as an exercise. Okay, so we completely kind of understand what's going on with degree 2. Basically, there is nothing kind of new for degree 2. Log concavity is the same as real stability. Let me immediately prove one thing. So now that we have this fact, let me prove this. Now let M, let M equal N comma I be a matroid of rank 2. Then I want to say that G of M, which is the G of M is basically log concave. So this is the special case of the theorem I said at the beginning. This is the only degree 2 case. So as we will see, the proof of the theorem I'm going to discuss is an inductive proof, and this will serve as the base case of the proof. Okay. So why is this true? So if you have a matroid of rank 2, you look at the generating polynomial of all bases. This is a 2 homogeneous polynomial. So I can write GM as Z transpose QZ because it's 2 homogeneous. So all I need to say is that, so by y above lemma, it's enough to show Q has at most n minus 1 negative eigenvalues, has at least, sorry, let's say this way, has at most 1 positive eigenvalue. Okay. How do we show that? So let's understand this Q. This Q here is nothing but the Hessian of GM. Okay. So Qij in particular, think about Qij, right? So we have a matroid of rank 2. What is Qij? Qij basically will be 1 if ij is a base of this matrix and it is 0 otherwise. Okay, so Qij is 1 if I comma j is a base and it is 0 otherwise. Okay, if it's a base, zi zj shows up in the generating polynomial, and therefore it's a base. Otherwise, it's 0. And in particular, on a diagonal, you always have 0, right? So because zi squared is not a base. Okay, so on a diagonal, I have 0. Now, so I have this 0, 1 matrix. I want to understand its eigenvalues. So how do I do that? Here's the idea. So I have to use the fact that I have a matroid. How is that used? So here is the main property. Let's say we say I and j are parallel if I comma j is not independent. So it's not in I, okay, or it's not a base in this case. So it's not independent. Let's go with that. This is in analogy with the notion of parallel edges you have in graphs. Okay, they also don't form an independent set in graphic matrix. Now, the main observation is that this parallel, this is a transitive property. Okay, meaning that if I and j are parallel, j and k are parallel, then I and k are parallel as well. Okay, I'm not going to prove this. You can just observe that it holds for a graph and prove it for any matroid in general. It follows from exchange properties of matroid. So this is a transitive property. So therefore, this partitions the elements of the matroid, partitions n, into parallel classes. Let's call them B1 up to Bm. Okay, so it means that B1, all elements in B1 are parallel, all elements in B2 are parallel, and so on. But more importantly, we get that any two elements which do not belong to the same Bi are not parallel, and therefore they form an independent set. So in particular, if I can arrange the rows and columns of Q such that I have, say, B1 here, the rows corresponding to B1 here, the rows corresponding to B2 here, and so on. Then I get this block diagonal matrix where every block I have 0, but everywhere else I have 1. Because again, if you pick two elements from the same block, you get they are parallel, but if you get two elements from different blocks, they are not parallel and they form a base. So this is exactly Q, and I want to say this matrix has at most one positive eigenvalue. So how would you prove this? There are many ways to prove this, in fact. So one way to see is that this matrix is the adjacency matrix of a complete bipartite graph. And any complete bipartite graph, its adjacency matrix has basically one positive eigenvalue. A more direct way to prove this is to write this matrix as the all ones matrix minus, let me call it actually J, the all ones matrix, call it J. J minus, let's call it J of B1 minus J of B2 J of Bm. Okay, by J of Bm, by J of B1, I mean this matrix which is all 1 in the B1 part and 0 everywhere else. Okay, so you can write this matrix like that. The thing is, J is a rank 1 matrix, and these J of Bi's are PSD. So you have a rank 1 matrix, and you're deducting PSD matrices out of it. So in other words, this minus sum of JBIs is a negative semi-definite matrix, and you're just adding a rank 1 matrix, and therefore that would only have 1 positive eigenvalue. Okay, so to formalize it, you need to use Cauchy interlacing theorem, which says that if you do a rank 1 update to a negative semi-definite matrix, it has at most 1 positive eigenvalue. Okay, so I'm not going to get into details. You can see the details in the notes. Okay, good. So we proved this. So we proved the base case. We proved that if you have a rank 2 matroid, again, let's look at the lemma. If you have a rank 2 matroid, then the generating polynomial of all bases is a log concave polynomial. Okay, so now we want to move forward. So how do we prove the main theorem that I promised at the beginning of the lecture? I want to prove for every matroid the basis generating polynomial is log concave. The natural idea that may come to mind is an induction, is to say that so matroids have this nice property that if you look at a matroid M, M slash I, this is when you contract I, this is when you, no, delete I, sorry, this is delete I, and M slash I, when you contract I. These are both matroids. Okay, with 1 less element. So normally that's one idea come to mind. Okay, so you get rid of 1 element, you have a smaller matroid, you know that it's log concave, and maybe you can induct. Okay, so we're not going to follow exactly this, but we're going to follow something similar to this. So before doing that, let me just first say a few simple facts about matroids, and then I'm going to formalize this induction. Okay, so basic facts about log concave polynomial. So fact 1, it's that again, if say P non-negative coefficients in Z1 up to Zn is log concave, then for any affine transformation, which you can think of it as something like AZ plus B. Okay, the property that I want is that it maps non-negative vectors to non-negative. For any affine transformation, if you look at P of AZ plus B, it is also log concave. Okay, so in particular, for example, these polynomials are closed under symmetrization. Like if you symmetrize 2 variables, put the same thing for both of them. You specialize to non-negative reals. So there's a difference here. I should say it's it's not true that log concave polynomial generalize kind of all real estate polynomials. You have to be a little bit careful because sorry, you have to be a little bit careful because here we are not allowing negative coefficients. Okay, so you don't also get to plug in negative, specialize to negative real numbers. You can only specialize to non-negative real numbers. But they're close under this, and also external fields. External fields. So basically, you get many of the closure properties of real estate polynomials here as well. Now, fact 2, it's that, so I'm not going to prove fact 1. It's part of a assignment, one of the assignments of this lecture. Now, fact 2 is that let's say you have P log concave and D homogeneous. Then and let's say Q is the Hessian of P at A, and again A is non-negative and P of A is non-zero. Then P is log concave at A if and only if, in other words, Hessian of log of P is negative semi-definite at A, if and only if the Hessian of P of A, which is Q, let's call it Q, has at most one positive eigenvalue. So this is exactly the fact we proved for degree 2. You can generalize this fact to any homogeneous polynomial of degree larger than 2 as well. Okay, so one test to see if a polynomial is log concave at some A is to check whether the Hessian has one positive eigenvalue at A. I'm not going to prove it. The proof is sort of similar. This one part of it similar to the degree 2 case that we did. The other part you need to do a little bit more work, but it's in the notes. You can read about it. Let me just say this third fact about log concave polynomials, and then we'll be ready to start talking about the inductive proof. So the third fact is about a necessary condition for a polynomial to be log concave. So I need a definition. We say a polynomial P is decomposable if it can be written as, say, P equal P1 plus P2, where, say, P1 is on variable, say, Z1 up to Zi, and P2 is on variables Zi plus 1 up to Zn. Okay, so for example, sorry, I should say, and we say it's decomposable, and we say it's indecomposable otherwise. Okay, so for example, here are two polynomials. One is Z1 squared plus Z2, Z3, sorry, Z2, Z3. The other one is Z1, Z2 plus Z1, Z3. Okay, which one is decomposable? The first one is decomposable, the second one is indecomposable. Okay, because the first one you can divide it into the part of completely based on Z1, the part based on Z2 and Z3. The second one you cannot decompose.
Do you also allow to other partition of the variables? I mean, of course, just because of permutationing.
Yeah, sorry, yes, any partition. Yeah, you're right. Sorry. Yeah, any partition is fine. Not just, yeah. So I should say maybe even Z2 squared plus Z1, Z3 is also decomposable. Yeah. Good. Now, very good question. Now, yeah, so the lemma is that if P is log concave, then it is indecomposable. So a necessary condition to get a log concave polynomial is that at least it must be indecomposable. Let me just prove this one. The proof is short. So suppose not, so we prove by contradiction. Suppose P is decomposable. If P is decomposable, say you write it as P equal, say Q plus R, and then Q has, maybe Q is on variables Z1 up to Zi, and R is on variable Zi plus 1 up to Zn. Then I want to write the Hessian of Q, Hessian of P. Here is the point. Hessian of P will be equal to Hessian of Q, 0, 0, Hessian of R. Where here we have the first I rows for Q, and the next n minus I rows, we have it for R. Okay. Now, here's the point. The point is by Frobenius theorem, this matrix has two positive eigenvalues. One coming from, so the eigenvalues of this matrix are the union of eigenvalues of Q and R, or of Hessian of Q and Hessian of R, because it's block diagonal. And because each of Q and R has non-negative coefficients, the Hessian of Q has one positive eigenvalue by Frobenius. Hessian of R has one positive eigenvalue. So this matrix has two positive eigenvalues, and that's a contradiction. So has two positive eigenvalues. So P is not log concave. Okay. Good. Okay, so now we said the background stuff. So now we know a little bit about these log concave polynomials. We're getting ready to prove the theorem. So as I said, we want to prove by induction. And for example, one idea is to note that, as I said, if you look at the matroid where you contract an element or delete an element, those are also matroids. So it's natural to expect that. So they must be log concave. So again, G of M minus I and G of M, you contract I, these are log concave. So, and you can write G of M as Zi, as G of M minus I plus Zi G of M slash I. So each of these two is log concave. So the whole question becomes, when can you say the sum of two log concave polynomials is log concave? Okay, and that's the type of question we want to study now. Okay, so let me, okay, I can just write down the theorem, but let me just motivate it for like a couple of minutes. I'm not going to prove the theorem, but I just want to motivate it how you may come up with this theorem. The proof is not really long, but I think the motivation is more interesting and more possibly useful. So how would you show sum of two polynomials, two log concave polynomials is log concave? Now you can ask, okay, how about real stability? We seem to know much more about real stability. Can we answer that? And in fact, even more, you can say, okay, maybe something even simpler. How about real rooted polynomials? How can you say sum of two real rooted polynomials is real rooted? So to understand that, you need this notion of interlacing. So we say, so let's say you have two polynomial P and Q. These are real rooted polynomials. And let's say the roots of this guy, the P, is alpha 1, alpha 2, up to alpha D. And this one is beta 1, beta 2, up to beta D minus 1. We say Q interlaces P. Actually, maybe even, let's see, yes. Interlaces P if basically alpha 1 is less than beta 1, is less than alpha 2, is less than beta 2, so on, less than beta D minus 1, is less than alpha D. Okay. So example, if you look at a real rooted polynomial, there's a polynomial P, these are the roots. And the polynomial looks like polynomial look. These are the roots of the polynomial. Then the derivative has one root between each pair of the roots. So the roots of a derivative are these circles. So and they interlace the root of a polynomial. Okay. Now we say one more definition. We say P and Q have a common interlacer. If there exists a polynomial R such that R interlaces P and Q. And now the fact here is a lemma. I mean, I'm a bit. I should say I'm a bit hand wavy here. I just want to give you intuition, so I don't want to be very concrete. So the lemma is that if P and Q have common interlacer, then P plus Q is real rooted. P and Q are basically, this is all about real rooted. So P and Q are real rooted and have a common interlacer, then P plus Q is real rooted. Okay. And in fact, this is if and only if any convex combination, so sorry, not only P and P plus Q is real rooted, any convex combination of alpha P plus 1 minus alpha Q plus 1 minus alpha Q is real rooted. And this is basically if and only if any convex combination of P and Q is real rooted, so they have a common interlace. Now, this fact that I just said, this is a fundamental fact in the proof of Caddison-Singer problem. Again, we're not going to get into it, but they use it crucially. This fact generalizes to real stability. Now, you can say that basically two multivariate, like a multivariate polynomial Q interlaces a multivariate polynomial P. You can say Q of Z1 up to Zn interlaces P of Z1 up to Zn if for all A positive and B in Rn, Q of AT plus B interlaces P of AT plus B. So in other words, Q interlaces P if along any line restriction, Q interlaces P. Okay, so the picture you want to think about here is that basically if the roots of Q looks like this, for example, then the roots of P, so this is roots of Q, roots of P looks like this, for example. Okay, if that's the case, then now you see any line like that that points to the positive orthant, the roots of P are basically any root of P is between two roots of Q. So they come one after, they alternate basically. Along any line pointing to the positive orthant, roots of P and Q alternate. Okay, and again, you have this similar fact that if you have a real scale polynomial, you take a partial derivative, say with respect to Zi, or even a directional derivative. So similar fact. If partial Zi of P interlaces P for real scale polynomial. Okay, so now we're going back to our original question. We wanted to understand when can we say sum of two polynomials, two real scale polynomials, for example, is log concave, or sum of two log concave polynomials. Sorry, sum of two real scale polynomials is real stable, or sum of two log concave polynomials is log concave. So I said that for real stability, you want to have a common interlacer, right? But how can you know that a polynomial is a common interlacer of two polynomials? So here is a consequence, basically. So consequence. Say you have a polynomial P. Sorry, before that, let me say one more thing. So this fact about partial Zi of P is in fact more general. Let me say this. You can look at dA of P. So what is this notation? This is a directional derivative. By this, I mean summation of AI partial Zi of P. And here A is non-negative. Okay. So again, dA of P basically interlaces P if P is real stable. And you need A to be non-negative. Okay, so this is a directional derivative. For example, partial Z1 plus partial Z2 is one such a thing. Now, okay, so now we go to the consequence I wanted. So suppose that dA of P is equal to dB of Q, dB of Q, and it's not equal to 0 for some A comma B non-negative and P and Q real stable. Then they have a common interlace. And P plus Q is real stable. Okay, I should say I'm a little bit again, as I said, this is a little bit informal. You also need one other condition for these statements. You need the polynomials to be monic. I'm avoiding hiding that under the log. Okay, under the log. But essentially, this is the gist of the argument. If you have two real stable polynomials which have a common interlacer like that, then the sum is real stable. Okay, or any convex combination is real stable. Now, this is the fact that we prove for log concavity as well. Okay, so we say that, sorry, let's call it a lemma. What was the lemma? Good. Suppose that P and Q are homogeneous log concave polynomial, and dA of P is equal to dB of Q, not equal to 0. By not equal to 0, I mean that it's not a zero polynomial. Okay, it's not a zero for A and B Rn. Then P plus Q is log concave. Okay. I should say, I'm going to assume homogeneity for almost all theorems I'm going to say about log concave polynomials. Some of these theorems generalize to non-homogeneous polynomials as well, but the theory is a bit more delicate there. So I'm not going to get into it in this course. Okay, so this is a lemma. This is lemma 410 in the notes if you want to look, but I'm not going to prove it. The proof is in the notes. I told you that it is the motivation that you may hope that this lemma is true, and once you have the right lemma, it's not so hard to prove it. Okay, so once you have this lemma, let me now explain the rest of the argument. Okay, so again, remember our goal is to show that the basis generating polynomial of any matrix is real stable, is log concave. So now we have the next lemma, which says that let P homogeneous, which is dehomogeneous, and indecomposable, then if partial Zi of P is log concave for all I, then so is dA of P for all A in A non-negative. Okay, so this is if a partial derivative of P is log concave, then any directional derivative of P is log concave. Okay, so this lemma immediately follows from the previous thing. Essentially, let me quickly sketch the proof. The way you prove it is basically by induction. You say that okay, let's fix this A. I know that A1 partial Z1 of P is log concave. Okay, by the assumption of the lemma. Now I want to use indecomposability. Okay, what does indecomposability say? Indecomposability say that there is no partitioning, that you cannot write P as sum of two polynomials with disjoint set of variables. So what that means is that if I look at partial Zi, look at pairs I comma j, such that partial Zi, partial Zj of P is not equal to 0. Okay, then these pairs form a connected graph. Indecomposability say that these pairs form a connected graph. Because if it is disconnected, you can write P as summation of two polynomials with disjoint set of variables. Now, once you have this, you have this connected graph. You can pick a spanning tree of this connected graph, and you can basically reorder the variables as follows. You can reorder the variables such that for all I, there exists j less than I, such that partial Zi, partial Zj of P is not 0. Okay. There is some variable before, such that partial Zi, partial Zj is not 0. You can just do this by picking a spanning tree and following a depth first search or breadth first search, and the tree is follows. So okay, so this is the main use of indecomposability theorem. Now let's do the induction. So I know that A1 partial Z1 of P is log concave. Now I want to do A1 partial Z1 plus A2 partial Z2 of P. How do I do that? I say that so by indecomposability, I know A1, I know partial Z1 partial Z2 is non-zero. Okay. I know partial Z1 partial Z2 of P is non-zero. Now I also know partial Z2 of P is non-zero. Okay. Now here's what you do. You look at let's let's look at yeah. Oh, wait. What do I see. I want to look at let's call this define C to be A1 partial Z1 plus A2 partial Z2. Then if I look at and B to just be partial Z to be A2 partial A2 partial Z2, then DC dB of P is equal to dB dC of P. Okay, and wait, I confused myself. These two are the same because you can reorder the differential operators, but no. What am I doing? This differential. So I have two. I want to have two. No, wait. Oh no. Oh, I see. No. I think I wanted this. I know that. Sorry, let's look at. Sorry, I think I defined C incorrectly. Let's say C is A1 partial Z1. So C is A1 partial Z1, B is A2 partial Z2. So I know DC dB is equal to dB dC, and that's not equal to 0. Now I can use the previous lemma to say that D of B plus C of P is non-zero. Okay. I mean, in other words, this is basic. Sorry, not that D of B plus C, which is really dB plus dC of P, is log concave. And I should say, sorry. This is non-zero, and so we have this fact. This is non-zero, and dB of P, dC of P, both of them are log concave. Okay, so dB of P is log concave, dC of P is log concave, and dB dC and dC dP are the same. So this says that the summation of dB and dC is log concave, and that's what we needed. Okay, so okay, sorry, this was a bit rushed. So this says this lemma, and now now there is one last lemma, which says that, I mean, this one is quick as well, but I'm not going to prove it. You can read the notes. It says that if P is dehomogeneous, and say P of A is not equal to 0, then P is log concave. If and only if dA of P is log concave at A, if and only if dA of P is log concave at A. Okay, so okay, so once you have this, you can now see how the inductive proof could go. If we have indecomposability, we know that all partial derivatives of P are log concave. This says that any directional derivative of P is log concave. And now, if P is log concave along a direction A, then P is log concave at A. That's the second. That's what the second lemma says. So now, once you have both of this, you can induct. First, you say that by induction, I know partial derivatives of P are log concave. This says that any directional derivative of P is log concave. And once you know a directional derivative of P is log concave, you can say P is log concave at that direction, at that point, at A. Okay. So okay, I'm out of time. Sorry, but the last. So when you put these lemmas together, you get to this theorem that if you have a polynomial P with non-negative coefficients, and it has the following two properties. First of all, if you take a partial derivative with respect to a vector kappa, say kappa is in Zn non-negative, and say with respect to S. S is a subset of N of P, and S has homogeneous. S is equal to D minus 2, is log concave. So whenever you differentiate P D minus 2 times, you get a log concave polynomial. That's the first property. And the second property is that partial S of P for S less than or equal to D minus 2 is indecomposable. Then P is log concave. So in other words, what I'm saying is, you give me a polynomial which is dehomogeneous. Here is a test to see if it is log concave or not. Look at all partial derivatives until you get to degree 2. Check that those are log concave. Look at all partial derivatives of not to degree 2, up to any degree, less than or equal to 2. Differentiate once, twice, some number of times, such a degree is still at least 2. You want all of those to be indecomposable. Then the same induction works. Okay, and shows that P is log concave. For the matroid case, we verified the A part. We didn't verify the B part. You can do that as an exercise. But basically, by the thing is, if you start with the basis generating polynomial, you differentiate some number of times, you still get an indecomposable polynomial. And now you can do the induction we just talked about. You can start with the degree 2, go up and up until you get to the basis generating polynomial. So this says that the basis generating polynomial is log concave. Okay. Sorry, we went out of time. Let me stop here. Let me know if you have questions.
Okay, thank you, Shayan. Are there any questions?
Can I ask a question that's slightly tangential, possibly?
Say again?
Can I ask a question that's slightly tangential to the main?
Sure, go ahead.
So somehow log concavity is generalizing real stable. And for real stable with positive coefficients, you know exactly where the zeros lie when you specialize. Like like you proved for the matching polynomial.
I mean, I know that the zeros are real, but I mean, I don't know how to calculate them.
not calculate them, but you know where they lie in the complex plane.
Sure.
And for log concave, I think you don't really know that. Is there some?
Yes.
Is there some intermediate class where you can say maybe the zeros lie in a cone or something like this?
So I should say two things. So for log concavity, you cannot hope to characterize them as the location of zeros. So there are examples of polynomials that are not log concave, but when you multiply them with some other polynomial, they become log concave.
I see.
So note that when you multiply, you just take the union of the roots, right?
Yes.
So there are polynomials which are not log concave, but when you multiply them, you get log concavity, and therefore you do not hope to get a characterization based on the roots. On the other hand, the question you asked about sort of cone roots, that's a good question. There are some groups of people who are studying these objects. Still, I think nothing is out in the archive, but probably in a few months we'll see some results. I know that some people are studying it, so sort of some generalization of real stability where you don't have the full, half, upper half complex plane or half plane. You have just the cone with some degree. That's, yeah, people are studying it. I think we should see some results.
Okay, that sounds very interesting.
Any other question?
Any other questions? Okay, so if not, then let's meet again tomorrow for Shayan's last talk, and of course.
And maybe tomorrow we may have to go a little bit over time because I just want you to warn you. I may have to go like 15 minutes over time. It's the last lecture, but yeah, just plan for that. Okay. Have a nice rest of the day.
Thanks for telling me.
Bye.
Okay. So thank you and bye everyone.
Bye.